recording. Okay, so it's recording now. And let me share my screen with you. So everyone can see my screen?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
All right. All right. All right. Okay. So let's start with
आवाज क्लियर नहीं आ रहा.
आपकी भी क्लियर नहीं आ रही. ठीक है, आ जाएगी. So I think, you know, probably some people can have internet issues. All right. So overall, you don't have to worry in the sense that, you know, this class is recorded actually. So I'll put this video lecture also. It's link on your LMS actually. So I mean, those who are able to understand, you know, all of it fully, good. I mean, if you think that you have missed some part due to poor internet connection or whatever, you can go back and download that lecture and, you know, see it at your convenience actually. Okay. So this lecture that we are doing will also be available on LMS actually. All right. So imagine you have, you know, a bunch of, say, sticks actually. Sticks are maybe, okay, so say wood pieces. So that's one wood piece. That's another piece of wood placed in front of it. Imagine that they all are of the, you know, same size. Okay. And they all are placed on floor, and so on and so forth. Okay. Maybe this is a pair of wood piece, stick, whatever you assume it. You may assume it. Okay. Okay. So they are placed right in front of each other. Okay. And have you seen? So how many have these dominoes videos actually? You may also treat them as dominoes. Have you seen dominoes?
No, sir.
You haven't seen.
No,
No,
sir.
you must have seen probably. You don't have that. What do you call? Okay, so here are the dominoes things actually. Dominoes. Can you see my the Google search that I am making?
Yes, sir.
Okay,
Yes,
so
sir.
Yes, sir.
Yes, sir.
dominoes play. You might have seen this. I don't know. That, oh yes. Yes, you might have seen all such videos actually that, okay, you place lots of dominoes in front of each other. Okay, and you know, throw one domino and you move one domino and the rest of the dominoes. All of these pieces are like the wood pieces. They all are, you know, they all are called dominoes. So you throw just one and everything will, you know, fall if it is placed correctly. Okay, so like that's called the dominoes game actually. So have you seen all of these?
Yes, sir.
Yes, sir.
It's like
Yes,
these,
sir.
Yes, sir.
like that's dominoes game actually. So when I am you know uh, you know, making this picture, so I am saying that imagine you have this series of dominoes placed in some order actually. Okay, and I'm asking from you to, okay, so here is the thing, where is the thing? So here is the thing that, okay, you have this series of dominoes, and imagine that the the dominoes are of the same height, they have the same distance between them, and they are in the ideal position actually. okay? And I ask from you, what should I do, okay? What should I do to make sure, to ensure that all of dominoes are down actually, okay? What steps should be taken to prove, to say that all of the dominoes are down actually? So what would be your response actually? Can someone of you give a response that, okay, what should be done actually, so that if I try to, for example, put down the dominoes, then I'll I'll say with the surety that yes, all of the dominoes are down now.
Sir, when we down one dominoes,
Mhm.
then all dominoes are downward.
Okay, so the first thing is that you must start actually. Okay. Okay, so the first thing should be that the first, okay, domino, okay, must be must be pushed down actually. Okay, so that's the first thing that happened. What should be the second thing? Is putting down first domino is going to be enough to prove that all of dominoes have been down actually? Hmm? Anyone else? So I want to prove with the surety that all of the dominoes are down. So, okay, the first domino should be down. What should be the second thing? Because the
Sir,
trouble
they automatically will fall.
is, like, okay, so that follows under an assumption actually, that what you are making an assumption that, if you throw one, if you push down one, all of them are going to go down. Like that's okay, that's assumption. So maybe you have a domino. Okay, so maybe this situation can also arise, that you have a domino and there is another domino which is away from this domino actually. And if this falls, then there is no impact on this domino. So
Yes,
saying
sir.
that,
But before,
but
but sir, before you said they are at equal distance.
equally spaced, and so on and so forth. So to make sure, let me add. So if someone want to add, otherwise I'll try to put the answer to make it precise actually. Okay. So what should be the second point? The second point should be that if we
Second
can,
domino should be down.
second domino should be down. Only second.
One by one, we will put all down, sir.
One by one, they should go down. So how about if I say that the first domino is down, okay? And how about if say that for a pair of domino, so imagine if you take any pair of domino, like 1, 2, or 2, 3, or 3, 4, or for k and k plus 1th domino, okay? For every pair of domino, if I prove, if I say that for every pair kth and k plus 1th pair of domino, okay, if, and that's a big if, the kth domino is down, then the k plus 1th domino is also down. Okay, so if I prove two facts, okay, if I prove two facts, the first fact is that the first domino is down, okay, and then I prove no matter what pair of domino you take, okay, no matter what pair of domino you take, first, second, or second, third, or kth k plus one, if the kth domino is down, this is going to push the k plus one domino to to go down as well, actually. Okay? So this is going to make sure that all of the dominoes are down. So if I can prove, if I can show, if I can demonstrate that first domino is down, in other words, the process has been initiated actually. Okay, so the process has been initiated. In other words, that the first domino has gone down, and then I prove that no matter what pair you take, okay, for every pair, if the first domino is down, then the next domino is also down actually. So if I can prove this for every pair, what will happen? I have proved that the first domino so the first domino is down, then, since the first domino is down, so the second would be down. And since the second is down, and I know that this second part is true, so the third domino would be down. And if the third domino is down, then since the second part is true, then the fourth domino would be down, and so on and so forth, actually. So these are the two conditions, okay? If I can prove these two conditions, then I can say with the certainty that all of the dominoes are down, actually. So do you agree with it? Yes, yes. Sophia, you may ask the question. Yes.
Sir, last domino is some distance. Then, sir, how the domino is?
No,
put down?
I'm not saying it. So in other words, if the last domino has some distance and the last domino is, not down, this means that this second part is not true. Okay.
Yes, sir.
Because
Yes, sir.
you have found a pair for which the kth domino is down, but not the k plus one. So I'm saying that if these both principles, these both conditions are true, then all of the dominoes are going to be down no matter where they are actually. Okay. And this is precisely the principle of induction is. That's how the principle of induction, principle of, okay, I don't know. The principle of induction works. Okay. Precisely. Principle of induction works. Okay. So what does principle of induction says actually? Okay, roughly if I say. So if is there any question in this description of dominoes, then I can move to the principle of induction.
No, sir.
Okay. So if there is no question, then let's move on. So imagine I replace each domino by a statement actually. So for example, P of 1 is a statement about 1, and P of 2 is a statement about 2, and P of 3 is a statement about, the number 3, and so on and so forth. And then I have a statement P of k, which is a statement about the natural number k. And then I have a statement P of k plus 1, okay, and so on and so forth. So this is like an arbitrary pair. This pair can be 1, 2, this pair can be 2, 3, this pair can be any pair. Okay, so this is a general representative of all pairs actually. Okay, so the principle of induction says that if P of 1 is true, okay, if the statement about 1 is true, okay, the P of 1 should be true. And the second thing is that if P of k, the statement about the natural number k is true, then the P of k plus 1 must also be true. The statement P of k implies P of k plus 1, no matter what k you take from the set of natural numbers actually. In other words, this first P of 1 is true is like, pushing down the first domino, okay? And like P of k implies P of k plus 1 means that every previous, statement is implying the next statement actually. So what would be the natural consequence? The natural consequence is going to be, I know that the P of 1 is true. And since the part 2 is true, so the P of 1 will imply that P of 2 is true. And again, from part 2, the P of 2 will imply that P of 3 is true, and P of 3 will imply that P of 4 is true. Similarly, every P of k implies that P of k plus 1 is true. So what would be the natural conclusion? Okay, so what should be the natural conclusion? The natural conclusion would be then, okay, that the statement about n is true for all natural numbers actually. That's really the principle of induction actually. Okay, so principle of induction is really an if-then statement actually. Okay, in which you have to verify these two conditions. First, that the P of 1 is true, and then you have to verify that every kth statement implies, if you assume kth statement to be true, then it implies the k plus 1th statement actually. Okay, so if these two conditions are true, then the P of n is true for all natural numbers actually. So this principle is called the principle of induction, and this is really like these dominoes actually. Okay, this is really like this domino process that, okay, if I want to say that all of the dominoes are down, okay, then what can I prove? I must show that the first domino is pushed and it's down, and then every domino is pushing down its next domino. So if I can prove these two facts, then it is enough to demonstrate, it is enough to show that all of the dominoes are down. Okay, so using this analogy, I have wrote what do you call the principle of induction. So if you have understood principle of induction, let me do one example on it, and then I will also prove this principle of induction, that why this principle of induction is true. So is there any question on it? Have you understood the principle of induction?
Yes, sir.
Yes, sir.
Yes, sir.
Good. You may also reply in chat actually. I mean, if you think that, okay, so you can also say yes quickly in chat actually. So, I mean, if you have question that that you want to ask quickly, so you can also say and ask in chat actually if you wish. All right, so so this is the precise statement, okay, and like this is an explanation. So you might have seen this induction in your FSC classes, and I don't know, you must be thinking and pondering actually that, okay, first you are proving for n equal to 1, and then you are saying that, okay, prove it for k plus 1 by assuming that it's true for k. Okay, so you might have seen all such
Yes, sir.
such things actually in your classes, but now we have kind of formulated it precisely. Okay, and the principle of induction is talking about basically an infinite number of statements actually. So this is something interesting, that you are proving an infinite number of statements, okay, and the statements are in such a way that they are implying each other actually. Okay, so it's an infinite number of statements that we are proving. So let me show you, and let me do one example based on it, or maybe some examples based on it, and then we can go ahead more actually. Okay, so let's do one example. So, here's the famous statement actually. Imagine you have this sum. Okay, so maybe you have this sum, the sum of the first n natural number 1 plus 2 plus 3 and so on and so forth, plus n is equal to n times n plus 1 upon 2. Okay, so there's a beautiful story behind, you know, this sum actually. There was a guy who's called Gauss, Carl Friedrich Gauss actually. Sometimes called the Prince of Mathematics actually. He was a very interesting guy. So, you know, when he was very young, you know, and his class was, you know, making a lot of noise, then his teacher in the class gave, you know, to engage them, gave them one problem actually, that, okay, do this sum, 1 plus 2 plus 3 up to plus 100 actually. Okay. And, you know, class thought that, you know, the teacher thought that, you know, they're gonna do this straightforward, like they're gonna do this in the way that, okay, 1 plus, the class is going to do in the way that 1 plus 2 is 3 and 3 plus 3 is 6 and 6 plus 4 is 10 and so on and so forth. So in that manner, they'll be engaged for a long time actually. Okay. But in the same class, there was Gauss actually, so who really came after really short time actually and came up with an answer for this sum actually. And the teacher was puzzled actually that how he did it quickly. Then he said that basically I observed this pattern actually. So he observed this pattern actually, that, okay, you know, if you add the first n natural numbers, then their sum is always going to be n times n plus 1 upon 2. So I observed this pattern and then I just quickly, you know, proved, the Gauss proved actually, that this sum is going to be 100 times 101 divided by 2. Okay, so whatever this number is going to come is the sum of these numbers actually. Okay, so this you know, result was a consequence of his observation actually. Anyway, so that's in the statement, and the statement is true. The statement is claimed that, okay, the sum of the first n natural numbers, okay, I don't know where I am, natural numbers, for all natural numbers is equal to n times n plus 1 upon 2. Okay, so I want to prove this statement by, you know, mathematical induction actually. So how I need to prove? Let's give this entire statement a name. So let's call this statement P of n. So whenever I am gonna say P of n, I'm gonna mean that I'm saying that, okay, 1 plus 2 plus so on and so forth plus plus n is equal to n times n plus 1 upon 2. Okay, so that is my statement P of n. So I have given it name actually. Okay, and I want to apply principle of induction to prove it. So first of all, I need to prove this, that, okay, that the P of 1 is true. By the way, these two steps have name actually. So this step, this first step, okay, is sometimes called, or you might also see in book actually, that this is also called a basis step actually. Okay, so that's a basis step. Okay, and this second step is called the inductive step actually. Okay, that's just inductive step. Anyway, so let's prove the basis step for you know, for this set of for this statement actually. So in order to prove the basis step, what we need to do, basis step, what we need to do, you need to verify the given statement for n equal to 1. In other words, we need to show that P of 1 is true. Now, what is P of 1 by definition? So in other words, you know, take the sum of the natural number up to the first natural number. Now, what is the first natural number? So it's 1 actually. So on this side, I'm going to take only 1. What will be on the other side? The other side, so since the n is 1, so it is going to be 1 times 1 plus 1 over 2 actually. Okay. And I don't know. So what will be this? So this is going to become 2 over 2, so that both sides are equal. The left side is 1 and the right side is also becoming 1 actually. So what does this show? That the P of 1 is true actually. Okay. By the way, to be sure, you can also check that whether the P of 2 is true or not. This is not required actually in, in principle. Okay, but to really have fun, you might also check actually that, okay, is the P of 2 is true. So what would be the P of 2? The P of 2 is going to be that, okay, from this side, take the first 2 natural numbers and their sum, so 1 plus 2. And from this side, put n equal to 2 in the inequality. So 2 times 2 plus 1 and everything divided by 2. So you can again see that this side is giving you 3 and this is also becoming 3. So the both sides are equal. So this shows that the basis step is true. Okay. The basis step is true actually. And by saying that the basis step is true, it's like, okay, you have pushed the first domino. And now what we would like to do? We will like to verify the second step of the principle of induction. And what is the second step of principle of induction? That if assume that the statement about the kth natural number is true and prove that it will be also true for the k plus 1. So assume this and prove k plus 1. So let's do the inductive step. Inductive step. Okay. So in inductive step, let's assume P of k. Okay, P of k. And what is P of k? The P of k is that, okay, let's assume that the sum of natural numbers up to k is equal to k times k plus 1 over 2. Okay. Maybe I should use some other color. K times k plus 1 over 2. And we want to prove, what? P of k plus 1. And what is P of k plus 1? That the sum of natural numbers, up to k plus 1 is equal to what? K plus 1, k plus 1 plus 1 over 2. So this is what that we would like to prove. We have assumed this and we want to prove this actually. So this, if I can prove this, then the both conditions of the principle of induction are going to be true actually. So how to prove it? So let's take, for example, this side and prove that why this side is equal to this side actually. Okay. So what is the left hand side of the equality that we would like to prove? So it's 1 plus 2 plus 3 plus so on and so forth, and plus k plus 1. Okay. By the way, what will be the previous term? So if this is k plus 1, what would be the previous term actually in this sum? The previous term is going to be
K.
k actually. Good. So it is going to be k. So I don't know that what is this entire sum from 1 to k plus 1. This is unknown to me. But by assumption, I know that this sum 1 to k is equal to k times k plus 1 upon 2. In other words, I don't know what is this entire sum, but I know this part of the sum, that what is this by assumption. So by assumption, this green part is equal to k times k plus 1 over 2. And the last term is really what do you call k plus 1. And now I would like to simplify this expression, and I want to say that whether I get this or not actually. So how can I simplify this expression? You know, I can pull out this k plus 1 out of the sum. Okay, so what I'm gonna get k over 2 plus 1, and if I simplify it a bit, I'm gonna get k plus 1 and k plus 2 divided by 2 actually, which is precisely this statement actually. Okay, which is precisely this statement. So what did I showed? I showed that if I sum from 1 to k plus 1, okay, then the sum is going to be k plus 1, k plus 1 plus 1, in other words, k plus 2, and everything divided by 2. But in order to prove this statement, what was the crucial thing that helped me? The crucial thing was this P of k actually, that, okay, assume P of k is true, and using that, we proved the P of k plus 1 is true actually. So the both, by principle of induction, the both if part, you know, the properties of the principle of induction, both conditions of principle of induction has been are true actually. Okay, so the first and true, so we can safely conclude actually that the P of n is true for all natural numbers, and hence what is P of n? The P of n is this statement, and I can say that this statement is true for all natural numbers. So that's really the proof by induction actually. Okay, proof by induction. So first, prove that your given statement is true for 1. Okay, and prove that every kth statement is implying is pushing the k plus 1th statement to become true actually. So if you can prove this by induction, the principle of induction, the entire statement is true actually. Okay, the entire statement is true. So if you have any questions on it, you may ask. Otherwise, I'll do another example. इसमें कोई सवाल है तो जरूर पूछें.
सर ये नीचे वाली लिखे हुए शो करें.
ये तक नहीं बनी. नीचे वाली, ये वाली
सर ये शो करें नीचे.
हाँ हाँ
सर ये थोड़ा एक मिनट.
फिर भी खड़े नहीं थे.
रेड लाइन के बाद वाला स्टेप,
ये वाला स्टेप जो है, नहीं ये तो चलो एक और मिसाल करते हैं भी समझ आ जाएगा. इसमें मैंने क्या किया है, P of n, क्योंकि मुझे ये पार्ट प्रूफ करना था, so I need to prove this actually. So इस स्टेटमेंट के मुताबिक assume P of k and using P of k prove P of k plus 1. यही if then statement का मतलब होता है. That's what is the meaning of if then statement actually. So I assumed P of k that, and what is P of k? The P of k is really the statement that the sum from 1 to k is equal to k times k plus 1 upon 2, and then using this we want to prove pk plus 1, which is the statement that the sum of natural numbers from 1 to k plus 1 is equal to k plus 1 times k plus 1 upon 2. In other words, wherever I had n, I just replaced k plus 1. Okay, that's what we will like to prove. And then in the last step, I have really proved it. And how did I prove it? I took the left-hand side and I said that using the left-hand side, the right-hand side can be, can be obtained actually. So I took left-hand side, okay? And so the left-hand side is the sum from 1 to k plus 1, okay? So like that's what is the left-hand side. And then I said that, okay, if you have this number k plus 1, the previous term is going to be plus k. Now, I don't know that what would be this entire sum from 1 to k plus 1, but I know by assumption that 1 to k, the sum from 1 to k is k times k plus 1 upon 2. So on the place of this, I substituted k times k plus 1 upon 2 plus k plus 1 is as it is actually. So I haven't changed it. And then I simplified this expression. I got what I want actually. So this kind of shows that the both conditions of principle of induction are true. So therefore, the P of n is true for all natural numbers. ठीक है मेरे भाई?
सर सिंप्लीफिकेशन से इक्वल नहीं आता है सर.
क्या बता? हाँ.
सिंप्लीफिकेशन से इक्वल नहीं आता है.
सिंप्लीफिकेशन से इक्वल नहीं आता? What do you mean by कैसे इक्वल नहीं आता?
सर एलसीएम ले ले 2k बनेगा, फिर ये k से इक्वल आएगा.
एलसीएम k और 2 और प्लस 1 का?
हाँ सर, k और k प्लस 1 है, डिवाइड बाय 2 है, प्लस k प्लस 1 है. एलसीएम ले लोगे 2 उधर मल्टीप्लाई भी होगा और डिवाइड में रहेगा.
नहीं आप तो एलसीएम इसका लेंगे
सर. तो 2k
नहीं ये तो आप, so you are taking the LCM of this part actually. So this is going to be k plus 2 divided by 2, and this divide is in the denominator of the entire expression. ये पूरे expression के divide में जी.
सर हम उसके ऊपर वाले स्टेप में तो एलसीएम नहीं लेंगे.
इसमें ले ले LCM, doesn't matter.
2 प्लस
इसके ऊपर वाले स्टेप में यहाँ ही ले ले LCM, doesn't matter. So you can take LCM here, doesn't matter. You're still gonna get the same result actually. Anyway, so this is elementary fact. Like, okay, do this algebra for yourself. Think about it, and let me do another example actually. Okay, so what we just proved is that the sum of the first natural numbers is always equal to n times n plus 1 upon 2, and we proved it through the principle of induction. So let me prove another identity. There are some identities that you should always keep in head. Okay. So for example, now let's prove another identity. And this is called 1 plus 3 plus 5 plus so on and so forth plus 2n minus 1. So this is equal to n square. Okay. So you can say that this is really the sum of first n odd numbers actually. Okay, odd numbers. And it says that if you sum the first n odd numbers, this sum is always going to be equal to n square. And what is this n? The n is the same n that you have here actually. Okay. So if the last number can be written in the form of 2n minus 1, whatever this n is here is going to be, this is going to be equal to n square actually. Anyway, so that's really an interesting kind of relationship actually. So you can verify it. Okay, so 1 plus 3 is going to be what? Is going to be 4, but the 3 can be written as 2 times of 2 minus 1. So if I take the 2 square, you still get 4 actually. Okay, so we need to prove this identity. And how we will like to prove the, and this is true for all natural numbers. No matter what natural number you take, this is true. Okay, and how we're gonna prove? We're gonna prove it through principle of induction, principle of mathematical induction. So how can we prove it? So first you need to take this statement 1 plus 3 plus 2n minus 1 equal to n square, and give it a name actually, that okay, this is a statement, this is an equation to whom I am calling it P of n. Okay, and I would like to prove this for all natural numbers. So first I need to do what? By principle of induction basis step. And what would be the basis step? That verify that the P of 1 is true. Okay, the P of 1 is true. By the way, what would be P of 1? By P of 1 means take the sum of first odd number actually. So what is first odd number? So the first odd number is 1. Okay. And now, what should be the n for the first odd number actually? So I can write 1 as 2 times of 1 minus 1. Okay. So the n for the first odd number is really, you know, is 1. This is your n. So if the expression ends at 2n minus 1, this should be equal to n square. Okay. So on the other side, what do you have? You have 1 square. The question is, are these two equal? The answer is yes, they are equal actually. So if they are equal, the P of 1 is true actually. Okay. So this is really a trivial kind of an example in which you don't have any complication, but to make sure, okay, to have a more clarity, let's think about P of 2 actually, the statement P of 2. So by P of 2, I mean take the first 2 odd numbers and see that their sum is equal to 2 square or not actually. Okay, so if this statement is true, so the answer is that yes, the second statement is true. So 1 plus 3, and I know that 3 can be written as 2 times of 2 minus 1. So this is like my n actually. So if I square this n, yani 2 ka square, then these two things are equal actually. Okay, so this shows that the P of 2 is also true actually. So P of 1 is true, P of 2 is true. So, you know, the basis step is really, what do you call, true. Is this step making sense to you? Any question in it?
No, sir.
समझ नहीं आ रही है? So what is
Are you
something?
समझ?
आ रही है समझ? So
Yes, sir. आ रही है समझ.
आ रही है ना समझ? So if you have question, please do ask. So next
Okay,
step is really, you know, the second step, which is that prove that P of k implies a P of k plus 1. Okay? And you have to, you know, remind actually that what is meaning of A implies B. The meaning of A implies B is that assume A and prove B. So if A, then B. Okay? Assume A, someone has probably asked. Okay? So let's assume first what? Let's assume first, I don't know, assume P of k. And what is P of k? The P of k statement is, so I have given P of n name to this, you know, description. So it's 1 plus 3 plus so on and so forth, plus what? 2k minus 1, and this is equal to what? K square. All right, that's the P of k. And we want to prove what? We want to prove P of k plus 1. That is, what is P of k plus 1? 1 plus 3 plus 1 and so forth, plus 2 times of k plus 1 minus 1. Okay, so wherever I have n, I just substituted k plus 1. And this is equal to k plus 1 square. So this is something that we have to prove actually. Okay, so if we can prove this statement, we are done. And how I'm gonna prove this statement? I'm gonna take this, I don't know, this left-hand side of the statement, and using my assumption, I'm gonna prove that this left-hand side is equal to the right-hand side. Okay, and the trick is what? The trick is pretty straightforward actually. So you have this 1 plus 3 plus so on and so forth, plus what? 2 times of k plus 1 minus 1. In other words, if you write this 2 times of k plus 1 minus 1 what? Explicitly, so it is going to be 2 times of k plus 1 minus 1 is really 2k plus 2 minus 1, so it's 2k plus 1 actually. Okay, so 2k plus 1. So can you tell me what would be the previous odd number if this is 2k plus 1? What would be the previous odd number actually? So if you want to from a
2k plus 1.
no, previous odd number. If you want to find a
2k minus
previous
1.
exactly, so just subtract 2. So if you take for example 5, you take 5 and subtract 2, you're gonna get 3, which is previous. And from 3, if you subtract 2, you're gonna get 1 actually. Okay. So if you subtract 2 from a given odd number, okay, you're gonna get what? The previous term. So the previous term, the hidden term that you have to write explicitly is 2k minus 1 actually. Okay, so this is the previous odd number. All right. So see that I haven't changed anything. I have just wrote the same thing and I just wrote the previous term, like the example that we did previously. Okay. And now, I don't know what is this entire sum. I don't know what is this entire sum, but I know that what is this part of the sum. Do we know this?
Yes, sir.
And what is this part of the sum? So it's k square. Okay. So by assumption, this is okay. By this assumption, this entire part is k square. Actually, this part is k square plus. So what is it going to remain here? So it's going to be 2k plus 2 minus 1, and everything is going to be k square plus 2k plus 1. And what is this? This is nothing but k plus 1 square. So what did I show? That if I take this side, okay, so if I take this side and compute the sum of it, it turns out to be k plus 1 square. In other words, this is your required identity. Hence, this shows that if we assume p of k, this is going to imply the p of k plus 1. Okay? That's an important thing to realize. We have to always prove the truth of p, the statement p of k plus 1, using the truth of p of k actually. Okay? And that's what we have done in this example and the previous example as well. Actually. Okay? And now since the part 1 and the part 2, or the both of the steps of principle of induction are true, okay, so you're gonna say finally, okay, finally you're gonna say that hence by principle of induction, p of n is true for all n in n, and that's it. That's really the proof actually. Okay, so that's what you have to. So first, verify that the given statement is true for a specific numbers, say n equal to 1 or n equal to 2, whatever, and then prove that every p of k is going to imply p of k plus 1. In other words, try to prove the truth of p of k plus 1 using the truth of p of k. So if both conditions are true, the principle of induction is true actually. Okay, I have already uploaded one exercise sheet on LMS. You can watch it, you can see it actually. Okay, and there are several such exercises on it. So we're gonna do more examples. So today we're gonna do a lot of examples actually on principle of induction actually. So is there a question on it? Is there a question on it?
No, sir.
सर थोड़ा 2 मल्टीप्लाई टू k plus 1 minus 1 is equal to k plus 1. यहाँ पे थोड़ा कंफ्यूजन, ये कहाँ से आ रहा है?
ये यहाँ से आ रहा है कि ओके दिस 1 to 3 2k minus 1, इसकी जगह मैंने रिप्लेस कर दिया k square and I just kept this as it is. ये जो एक्सप्रेशन है ये यही है ना, So 2 से multiply कर दिया, you have 2k, 2 times plus 1, 2, and minus 1 is 1. And 2 minus 1 is gonna be 2 plus 1. So I just rewrote the same expression. So on the place of this, I use the assumption that this is equal to k square, and this rest of expression that I am having is really the same as this actually. So I'm not doing anything new. So added and simplified this expression when you added k plus 1 square. Okay, that's what is really the way to do the things.
Okay, sir.
Okay, so let's move on. Before moving on, now I would like to really prove what the principle of induction itself. But before moving that, there are some important sums that you should always keep in head, that 1 plus 2 plus 3 plus so on and so forth, n is equal to n times n plus 1 over 2, and 1 plus 3 plus 5 plus I don't know 2n minus 1 is going to be n square. By the way, what would be 2 plus 4 plus so on and so forth plus 2n? Can someone tell me? Do I need to prove this? Anyone? What would be 2 plus 4 plus 2n? Any guesses?
n plus 2.
N plus 2. Even number hai. N plus 2. Okay, so that's one guess. How about anything else? So I mean, if you think a bit cleverly, so this is not difficult. Think about it. So 2 plus 4. Any guess before I write? So see, if you pull out the 2 from all of these numbers, 1 plus 2 plus, so you're gonna have plus n actually. And I know this sum. So it's 2 times of n plus 1 times n by 2 actually.
N plus 1 divided by 2.
So it's gonna be n times n plus 1. So the sum is really, sum of even numbers is n times n plus 1. So you don't have
N plus 1.
Okay, that's a recipe. Okay, that's really a party trick actually. You can say your younger brother, okay, and you can impress him. Okay, give me the numbers from 1 to 1000. Okay, and say him to pick the calculator and do the sum actually. And you can you can do this sum very quickly. Okay, and in that manner you can have some treats from your younger brother, or you can impress your younger brother. Anyway, so that's one thing. So this is proven, this is proven, this is also proven actually. Okay, so we don't need to prove it. The next is 1 square plus 2 square plus so on and so forth, n square actually. The sum of first n square. So this sum is, I don't know, I guess it is equal to, does someone remembers? Yes, it is, where is it? Okay, so I have to find out. N times n plus 1, okay, times 2n plus 1 upon 6 times 2n plus 1 upon 6. So this is the sum actually. Okay, so try to prove this, try to verify this by principle of induction. Okay, so this is something that you should keep. I should write it properly in a more manner. So I'm learning to myself to write how to write with this tablets actually. So sometimes they go crazy. So it's n times n plus 1 times 2n plus 1 divided by 6. Okay, so that's the sum of natural number verified by principle of induction. As we have proved previously, try to prove it for yourself. It's not difficult to do actually. And then you should also keep the sum of the cubes actually. 1 cube plus 2 cube plus so on and so forth plus n cube. And the sum is really easy. So the sum is really n times n plus 1 upon 2 square actually. Okay, n times n plus 1 upon 2 square. So in other words, so take this and square it actually. Okay, so it's really the square of it. So verify. Or you can also say that 1 cube plus 2 cube plus so on and so forth, and cube is equal to 1 plus 2 plus so on and so forth plus n entire square. Okay, so this identity is the both identities are saying the same thing actually. So verify this also by principle of induction. Okay, and these are the sums that you should have in your memory actually. Okay, because these are the very frequently used sums, so you need to use them in different places actually. You need to use them in different places. Okay, is there any question in it?
No, sir. Okay.
Okay. By the way, if I now say, so here's the thing. So let's see that how clever you are. If I now say that, okay, I need to find a formula from the sum of say 10 square plus 11 square plus so on and so forth up to n square. So I don't want to start from 1. Can someone tell me a way to find out this formula? What would be your trick to find out this formula?
Yes, sir. May I?
Yes, yes.
सर पहले सर 1 से लेंगे सर n टर्म तक और फिर सर उसमें से माइनस करेंगे सर 1 से 9 तक तो बाकी का जो होगा सर.
Yes, this is very clever actually. So in other words, you're gonna say, okay, I don't know the formula. I know the formula that starts from 1 actually up to n square. But how to find the formula for a number, for a sum that starts from 10 square and ends at n square? The answer is that you can still find through the same formula. And how you can do it? That okay, you take 1 square plus 2 square up to n square, okay, and subtract 1 square plus 2 square plus 1 and so forth plus 9 square. Do you agree that this would be true? And this sum is going to be what? This sum is going to be like, okay, n times n plus 1 over 6, all right, and what? Times 2n plus 1 minus what would be this sum? So by definition, so if the sum is from 1 to n square, you get n times n plus 1, 2n plus 1 upon 6. So you're going to have what? So n is 9 here. So you're going to say 9 times 10 times 2 times of 9, 18 plus 1, 19, and divided by 2. So that's really the formula. So if you simplify this number and simplify the expression, that would be the formula for the sum to sum from 10 to n square. Okay, so these are little clever tricks that you have to that you can use actually to find even those formulas for which you don't know, the explicit formulas actually. So you can drive it from here actually. Okay. So we will see a lot of such things in today's discussion actually. So if there a question in it, otherwise I would like to prove now the principle of induction. Okay, that's what is my next step actually. Any question here? No question? All right, so let's now do mathematics and try to prove that why the principle of induction itself is true. Okay, why the principle of induction is itself trustworthy actually. So why it is true actually. Principle of induction. What was principle of induction? The principle of induction was for given statements P of n, where n is from natural numbers. Say following is true. Number one, P of 1 is true. Number two, every P of k implies P of k plus 1, okay? For any k that is a natural number. So if these two conditions are true, then, or maybe I should write if here, then P of n is true for all n in n. That's really the principle of induction. Okay? And now I would like to prove this principle of induction itself. Okay, so what are the proof of this principle of induction? We are using a principle, we are using a method to prove the other things, okay? To prove the other interesting results. But the question is, what is the proof of this principle itself actually? The answer is, you can prove it easily. Okay.
अच्छा आगे एकड़ो पढ़ाया तो लाज वसमाओ जादो मुफ्ती है वो ए गाली तो और सागी कंदो टिप टिपा वाली
ये बेटा अपना ये माइक जो है ये ऑफ कर दें. Someone has on mic. ठीक है? Okay. Challenge. I thought maybe something interesting is coming out, but Anyway, so how we gonna prove this statement? So we want to use the method of contradiction actually, and I hope you remember method of contradiction. So what was method of contradiction? So by method of contradiction, if you want to prove A implies B, okay, you try to prove that its negation A implies B, which is A and not B, okay, this statement is false actually. So if we can prove that the negation of A implies B is false, then A implies B is true. And how we gonna prove that negation of A and the negation of B is false? We will show that A and negation of B, in other words, if you assume this, this will take you to a contradiction, take you to a contradiction actually. So anything that takes me to a contradiction, just throw it away. It must be false actually. Okay? So if A and not B takes you to a contradiction, then A and not B is false. And if it is false, what is true? Its original statement or its negation, which is the A implies B actually. Okay? So in this given statement, what is your A? Can someone tell me that in the principle of induction, what is A and what is B in principle of induction?
Sir, I think A is P
Last
of K.
And B is P of K plus 1.
Yes, sir.
pair, na sir, last pair.
Okay. Anything else? So see, this statement can be written as if A, then B. Okay, so this is what it is. So all of the if part is your assumption, your A, and all of the then part is your B. So the A is this actually, the 1 and 2. So if this is true, that's your A. And B is your this part. Okay, this is your B actually. Okay, so you have to learn to identify the parts as well. So if part is my A and then part is my B actually, and I want to prove that if A then B by method of contradiction. So what I need to do, I need to assume that its negation is true, and that negation should take me to a contradiction that will falsify the negation, and hence this will make the given statement true actually. Okay, so how should I now proceed to the proof, for example? So I'm gonna say that suppose, okay, suppose contrary that the statement 1 and 2 are true, but by the way, what would be the negation of this part B? Can someone tell me the negation of B? So the B says P of n is true for all n. What would be the negation of it?
P of n is false for some n.
Some n actually. Okay, so do all of guys agree that this would be the negation?
Yes, sir.
Okay,
Yes, sir.
good. Okay, good. So let me negate it. But there is, say, an index. There is a j in n such that P of j is false. P of j is false. समझ आ रही है बात? So that's really the contradiction. That is this part that I have written is really the negation of the principle of induction. That the condition 1 and 2, the assumption, the if part is true, but the conclusion is false. And what is the negation of conclusion? That P for some index is false actually. Okay, so I have called this index as J actually. Okay, all right. Now let's assume additionally, and this is important. So see, so imagine this is a step 1, this is a step 2, this is a step 3, so on and so forth. And I don't know, this is J. So these are some steps actually. Okay, so let me rewrite it to give you illustration actually. So this is, say, so these are some steps, for example. Okay.
Excuse me, sir.
Gigi.
Sir, can you please repeat from this part proof where we have supposed?
Which proof? What?
That we have supposed contrary that 1 and 2 are from this
Wait,
text. Can you
this
please
is okay. So let me say it again. Okay, let me say it again. So if you write this statement in if then form, so you have if A then B. Okay, if A then B. So A is these two statements. So that's if part, something that is coming with if. So this is your assumption, and the B is conclusion. So in method of contradiction, okay, in method of contradiction, you have to do what? You have to always say that suppose contrary that A is true, but B is false. Okay. In other words, assumptions are true, but negation is false actually. And why we are doing it? Because we know that the negation of the implication, is, I don't know what I'm writing. The negation of the implication is A and not B. In other words, assume A, which is if part, and negate B, which is conclusion. And that's what precisely I have done. Assume A is true and B is false. Now I'm saying that what is A here in this part? The A is the statement 1 and statement 2. So the 1 and 2 are true. And what is B here? The B is this actually, that P of n is true for all n. So what would be the negation of it? So I'm saying that a statement is true for all n. So the negation of it is going to be that there is some n, in other words, some natural number, let's give it a name j, okay, such that the P of j is false actually. Such that the P of j is false actually, okay. And as I said that there, so the negation of the universal statement is that there must be at least one n actually. There must be at least one n for which, the P of n is not true. Okay, let's give it a j. There can be many j's actually. So in other words, there can be many steps. So for example, that's 1, 2. Say for example, the ith, the P of I is false, and I don't know, P of 100 is false, rest are true, and the P of j is false. Okay, but I am assuming actually. So assume that j is the first index for which P of j is false. Okay, j is a first index for which P of j is false. So what do I mean by that? So let me say it more explicitly. So one is claiming that all of these are true. First statement is true, third is true, fourth is true, so on and so forth. What would be the negation of it? The negation of it is going to be no, the some are not true. Some of them are not true. So I don't know which of them are not true. So maybe the third is not true. Maybe the fifth is not true. I don't know. Maybe the 100th is not true. Okay. So out of all these statements, I'm taking the first statement, okay, which is not true. They can be afterwards a lot of statements for which, you know, the P of n is not true. But out of all these, I'm only taking the first statement, which is not true. And when I'm saying that this is the first statement which is not true, what do I mean? That all of the previous statements are true. Okay, so if the third statement, pehli statement, if the third is the first statement which is true, which is not true, that means I'm saying that, you know, all of the previous statement before the three are, what do you call, true actually. Ye samajh aa rahi hai baat? Is this something that you are getting, beta? That's an important part actually. The proof will work on this actually. So agar main ye kehta hu, so if I'm saying that the J is the first index, okay, so where is it? I don't know, where is it? So it's here. So J is the first index for which P of J is false. This means from 1 to J minus 1, all statements are true. And the Jth is the first statement which is false. And after this, there can be many statements which are true and false, but I'm only interested in the first instant when the given, statement is false actually. Okay, ये बात समझ आ रही है?
Yes, sir.
ठीक है ना? चलिए, अगर बस समझ आ रही है तो ठीक है, which is good. So if the J is first statement, now I can show you the contradiction actually. Now really I can show you the contradiction. Okay. Think about, by the way, can you see the contradiction? We are saying that what we are saying this, that you have a step 1, so on and so forth. So that's your step 1, 2, so on and so forth. This is J minus 1, and this is Jth step. In other words, this is representing P of 1, this is representing P of 2, this is representing P of J minus 1, and this stick is representing P of J. I'm saying this is the first statement, okay, which is false. This means that all of these statements are true. Okay, all of these statements are true. And we also know that 1 and 2, they both are also true. What is the meaning of 1 being true? That this statement is true. What does this P of K implies? P of K plus 1? For all K, this statement is true. This means that the statement 1 implies 2, the statement 2 implies 3, the statement 3 implies 4. No matter what pair you take from, natural number, always P of K implies P of K plus 1 equal to 2. P of K implies P of K plus 1. But now here is a contradiction actually. If the Pj minus 1, the J minus 1th statement is true, okay, and this principle is true, the second part. By second part, we should conclude that the P of J is true. Are you getting my point? If the J minus 1th statement is true, if the J minus 1th statement is true, and every K implies that K plus 1 is true, then this is going to imply that the Jth statement is also true. Now we had a trouble with the Jth statement. At one instance we are saying it is false. At other instance we are saying it is true. So that's a contradiction. That's a contradiction.
सर
हाँ भाई?
P of J
सर रिपीट करें प्लीज।
समझ में नहीं आया।
ये समझ नहीं आया, चले आप यू समझें. So let me show you this now. Let's not take it j and so on and so forth. So imagine you have this p of 1 statement, p of 2, p of 3 and p of 10 actually. फर्ज कर दें p of 10 is true. फर्ज कर दें p of 10 is the first statement which is false. ठीक है, एक ये इसको बेटा माइक को ऑफ कर दें जिसने भी ऑन किया है. ठीक है, फर्ज कर दें imagine that the p of 10 is true. ठीक है, p of 10 is false actually. 10वीं स्टेटमेंट वो स्टेटमेंट है which is false actually. ठीक है, 10वीं स्टेटमेंट वो पहली स्टेटमेंट है which is false. तो अब मुझे बताएं, when I'm saying that 10वीं स्टेटमेंट वो पहली स्टेटमेंट है which is false, what do you can say about all these 9 statements?
They are true.
They are true. ठीक है, यानी पहली स्टेटमेंट भी ट्रू है, दूसरी भी ट्रू है, 9th भी ट्रू है. और अब अगर मैं and I'm saying that the part 2 of the given statement is also true. Part 2 of the given statement के true होने का मतलब क्या है कि the statement 1 implies 2, the statement 2 implies 3, the statement 3 implies 4. Implies से क्या मुराद है? So if the p of 1 is true, then p of 2 is true. And p of 2 is true, then p of 3 is true. And if the p of 3 is true, p of 4 is true. And similarly, if the p of 8 is true, p of 9 is true. And if the p of 9 is true, by part 2, we get that p of 10 is true. Now that's a contradiction. पहले हम कह रहे थे, first we were saying that p of 10 is false. Now, if the statement 2 of the given assumption is true, so फिर the p of 10 has to be true as well actually. So p of 10 is kind of a strange statement, एक अजीबो-गरीब statement है जो true भी है और क्या है, false भी है. So that's a contradiction better. And why this contradiction is coming? This contradiction is coming that you have assumed something entirely false. This entire, ठीक है, contradiction, contrary assumption, ये जो assumption है, this is false actually, because this is taking you to a contradiction. And since this is taking you to a contradiction, this is false. So if this is false, this given statement is true. क्यों? क्योंकि this statement is a negation of the given statement actually. So therefore the principle of induction is true. So we proved the principle itself by the method of contradiction actually. इसमें कोई सवाल हो तो पूछें.
I have a question.
Sure, better, sure.
Sir, you said that P of 1 is a proof that P of 2 is true. Likewise, P of 2 is a proof that P of 3 is true. Sir, how do we know that?
बेटा ये part 2 true है ना. देखें हमने we have clearly stated बेटा, ये थोड़ा सा पढ़े यहाँ पर. Suppose contrary, बड़ा बड़ा लिखा हुआ है. Suppose contrary that the 1 and 2 are true. Let's assume that these two statements are true. अब इनको पकड़ लें अपने हाथ में कि P of 1 is true और हमने ये मान लिया है कि हर पिछला जो स्टेप है वो अगले स्टेप को ट्रू बना देगा. 1 2 को ट्रू बना देगा, 2 3 को ट्रू बना देगा. That's what we have assumed actually. और फिर हम ये कहते हैं कि ये जो कंक्लूजन है कि जी P of n is false, P of n is true, this conclusion is false actually. ठीक है? So since this conclusion is false, we have assumed the negation of it actually. ठीक है? That's the essence of what do you call method of contradiction actually. That कि आपके पास एक implication है, A implies B, you want to prove it, you have to assume its negation. और इसकी negation का मतलब ये है कि you assume that its assumptions are true, but the conclusion is false actually. That's what you have to assume, and that's what I have assumed. अब इसका if part जिसको मैं बार बार A कह रहा हूँ, I'm saying that is true, और इसका जो then part है जिसको मैं B कह रहा हूँ is false. That's what I have assumed. और क्योंकि A true है और A के अंदर ये दोनों हिस्से आ जाते हैं, these both 1 and 2 are coming actually, ठीक है, in the part A, so I'm assuming that they are true. So if they are true, then the conclusion that I have talked here is going to work actually, that the P of 10, the 10th statement is false because of this assumption, and it's true because of the second part of the assumption A actually. So P of 10 is a strange statement which is true and false at the same time. So therefore, just throw this, just throw this entire negation into the dustbin. In other words, this negation of the implication is false. And if the negation of implication is false, what is true? The implication itself. Any A implies B. Or A implies B kya hai? It's really your principle of induction actually. ठीक है बेटा? So that's what is really the essence of it. If you have questions, you can ask. I know it's a bit tricky, but it's not that tricky. इतना भी मुश्किल नहीं है. I mean, if you follow the argument carefully. I'll share another video actually with you, ठीक है, in which I am proving this on a board actually. So you can watch this again and again, and you can watch this recording again and again, and you can make sense of it. So first you have to keep in view that what is the meaning of method of contradiction, how method of contradiction works, and then I would like to apply the method of contradiction onto the principle of induction actually in order to prove it. Okay, and I have proved this principle of induction through the method of contradiction. So that's what is really the essence. And your task is not really to worry about the proof of principle of induction. Time principle of induction. The key thing that you have to learn is that how to apply the principle of induction on different things actually. ठीक है? कोई सवाल है तो पूछे, otherwise फिर आगे चलते हैं. By the way, if you want to take a break of 5 minutes, take a break of 5 minutes, and then we can start, some more problems through the principle of induction. Actually. Let's do the break. Okay, let's do 5 minutes break, and then let's meet after 5 minutes. Challenges. So let's get back and let's get benefit out of the principle of induction more actually. So, I mean, don't worry. I mean, if you haven't understood completely the proof of it, just go back, sit back and, you know, ponder over the proof of the principle of induction. Okay. And, you know, I know that it sometimes takes time to absorb it, but it's not that difficult. I mean, it's really logical. Okay. It's really logical. So the key thing that we have to, you know, do with the principle of induction is to apply it in a variety of situations. So let's do some more examples of a principle of induction actually. Okay. Okay, let's do this. Okay, so here's a beautiful lemma from your book actually. Okay. So here's a little lemma from your book, and it says this, that okay, let n be a natural number. Okay. And for this natural number, I say that n is bigger than or equal to 3. So it's a natural number that is bigger than or equal to 3. Okay. So we have to prove that that for any n bigger than or equal to 3, if you square it, this square is always bigger than 2n plus 1. Okay. Can you make sense of the statement? What does the statement is saying? So take any natural number bigger than or equal to 3. Its square is always bigger than or equal to 2n plus 1 actually. Okay. Is it making sense? So you take n equal to 3. So you're going to get 3 square, which is 9, and 2 times 3, 6 plus 1, 7. So the 9 is bigger than 7. Take n equal to 4. This is true. N equal to 5. This is true. The question is, can I prove this in general? The answer is yes, actually. Why not? You can prove it through the principle of induction. So let's prove it. And how should we prove? So first of all, let's give your given statement a name. Let's call your given statement as the, what do you say? P of n, and P of n is what? That n square is bigger than 2n plus 1. Okay, that's my statement that I have to prove for n bigger than or equal to 3, and obviously n are natural numbers. So that's my statement that I should do actually. So let's take the basis step. So what we should do in the basis step?
P of one के लिए prove कर देना sir.
So you have to now think carefully about it. So if you try to prove it for the P of 1, this must be false. Why? Because 1 square, on one side you have 1 square and on the other side you have 2 times of 1 plus 1 actually. So
Sir,
which?
so here P of 1 3 होगा ना? P of 3.
1 square and 3. So you have to, this statement is explicitly saying that, okay, try to prove this statement for n bigger than or equal to 3. So you have to start not from 1, but from 3 actually. 3 actually. So let's verify that is P of 3 true? P of 3 is true. Is it true? So in the given statement, substitute 3. So you have a 3 square on one side and 2 times of 3 plus 1 on other side. So 3 square is obviously 9, and 2 times of 3 plus 1, 7 is really is 7. So is 9 bigger than 7? The answer is yes actually. Okay, so you're gonna say hence P of 3 is true. That's it. Okay, so prove that. So it's not always necessary that a statement should always start from P of 1 actually. So it can start from anywhere mentioned in the domain actually. Okay. All right, the P of 3 is true. So that's the basis step. And then now we need to do the inductive step actually. So where is the inductive step? The inductive step. So help me out in inductive step. What should I do? So let's assume P of K is true. Okay, that is, what is the meaning of P of K? That K square is bigger than 2K plus 1. Okay, and keep in view that the K is bigger than or equal to 3. And we have to prove what? That P of K plus 1 is true. So we need to prove, that P of K plus 1 is true. That is, we need to show that if you take K plus 1 square, this is bigger than 2 times of K plus 1 plus 1 actually. Okay, this is what that we have to verify. And in order to prove this, I am allowed to use this inequality. Okay, so let's prove P of K plus 1. So how can I prove P of K plus 1? Any suggestion? From where should we start? So this is the inequality that we have to prove. So take the left hand side of say inequality and try to prove that it is bigger than the right hand side. In it. Okay, so take the left hand side. Now take K plus 1 square. So if I expand it, I'm gonna get K square plus 2K plus 1. Okay, K square plus 2K plus 1. Now this guy is greater than what? Can you give me a guess actually? So see, you know it from your assumption that K square is bigger than 2K plus 1. So if K square is bigger than 2K plus 1, then this number is bigger than what?
2K plus 1.
Okay, this is
16, sir.
2K plus 1 plus 2K plus 1. So So the k square is bigger than 2k plus 1. This 2k plus 1 is same as 2k plus 1. Okay. And this quantity is going to be equal to what now? Is going to be 4k plus 2 actually. And which is same as 2 times of k plus 1. Okay. Am I doing something silly? I hope not. I hope not. Okay. Okay. So what we have to prove? We have to prove 2 times of k plus 1. K square is bigger than 2k plus 1. Are we doing some mistake? Any suggestion? So here's the mistake. I think we need to put a 2 here. Actually. We need to put a 2 here. Okay, so we need to put a 2 here. And now, as previously, what we should do? Now, what we should do? You know, we saw previously that how to prove the inequalities. I know that k plus 1 is square. Okay, from my deduction is bigger than this number, but I need to prove that k plus 1 square is bigger than this number actually. So the question is, can I compare this number with this number? So if I can prove that this number is bigger than this number, then the k plus 1 square by transitivity will be bigger than this number actually. But how can I prove that this 2 times 2k plus 1 is bigger than 2 times of k plus 1 plus 1? So we saw the different ways actually. We can apply any one of the way. One of the way is that, okay, take the difference. So take the 2 times of 2k plus 1 and subtract what? This guy actually, and see that whether you get a positive number or a negative number. So if I subtract this, so 2 times of k plus 1, okay, and mine plus 1. So if you simplify it, what you're going to get? You're going to get 4k plus 2 minus 2k minus 2 minus 1. And everything that you get is really the 2k and a minus 1. Can I say 2k minus 1 is a positive number? Why 2k minus 1 is a positive number?
Yes, sir, because k is greater than or equal to 3.
Now, since so you have to show it explicitly. So since the k is bigger than or equal to 3, that means 2k is bigger than or equal to 6. That means 2k minus 1 is bigger than or equal to 6 minus 1. That is that 2k minus 1 is bigger than or equal to 5, which is bigger than 0. Okay, so this number is bigger than 0. So what does this show? That this first number is bigger than the second number actually. So we proved it. So what we proved, that k plus 1 square is bigger than this number, and this number is bigger than this number. So by transitivity, we proved that k plus 1 square is bigger than 2 times of k plus 1 plus 1 actually. That's really the proof. So we proved it through mathematical induction. Hence, I can say that P of n is true for all n bigger than or equal to 3. So that's it. That's what really is the proof actually. So is there any question in it? Is it making sense?
Excuse me, sir.
Did it?
Sir, can you please repeat from now we take how we started it, proving this?
बेटा फिर ये इसका मतलब है कि you haven't really understood the very first definition of principle of induction actually. ठीक है? I'm applying principle of induction. ठीक है? I have the principle of induction says, ठीक है? Let me repeat it. Let me repeat it again. You want to prove a statement P of n. You want to prove that P of n is true. So prove two things. Prove base is a step. Base is a step means what? Prove that this P statement is true for some concrete number, say 1 or 2 or 3 or whatever. So prove that the P of 1 is true. Okay. So for example, here we proved that P of 3 is true because everything is starting from n equal to 3. Okay. So we proved here the first step that the P of 3 is true. And then prove the inductive step. The inductive step. And the inductive step says that every P of k implies P of k plus 1. In other words, assume P of k and prove P of k plus 1. So we did what? We assumed the statement P of k, okay, that P of k is true, okay, and what is P of k? Wherever you have n, just substitute k actually. So the P of k is that, okay, k square is bigger than 2k plus 1. We assumed it according to inductive step. And then we tried to prove what? We proved that the P of k plus 1 is true. Okay, that's what we need to prove actually. So we proved it. How did we prove it? So in other words, what we need to prove that k plus 1 is square. Okay, so where is it? So k plus 1 is square is bigger than 2 times of k plus 1 plus 1. How did I get this statement? I just substituted n equal to k plus 1 in my given inequality that I have to prove. Okay, so if I substitute n equal to k plus 1 in my given inequality, I get this. But this is something that I have to prove. So how did I started the proof of it? So I started from the left hand side of this inequality, which is k plus 1 square. I expanded it. Okay, and now I said that I know about the k square, that this is bigger than 2k plus 1. So this means that this entire expression is bigger than what? Since the k square is bigger than 2k plus 1, so I kept it as it is. So I just wrote it. And this 2k plus 1 is same as 2k plus 1. Okay. So k square plus 2k plus 1 is bigger than 2k plus 1 plus 2k plus 1. And I got this expression, which is 2 times of 2k plus 1 plus 1. But I need to prove that k plus 1 square is bigger than 2 times of k plus 1 plus 1. So that's what I have to prove actually. But from my calculation, what I get is this expression. So if I can show, so this is like my I don't know, this is like my number A, and this is like my number B, but I want to prove that A is bigger than a number C. So in order to prove that A is bigger than C, it is enough to prove that the number B is bigger than number C actually. So what is B? Which is this number, and what is C? This is this number. So A is bigger than B, and if I can prove that B is bigger than C, then by transitivity A is bigger than C. And how can I prove that B is bigger than C? In order to prove that B is bigger than C, you need to prove that B minus C is equal is bigger than 0 actually. And that's what I have done. I took B and I subtracted C, and I proved that it is bigger than 0. So this shows that, you know, that B is bigger than C. Now, since A is bigger than B and B is bigger than C, so therefore by transitivity A is bigger than C. So I got the inequality what I want. Okay? So I'm doing this analysis, okay? But all of the previous knowledge that I have learned about proving inequalities and equations and principle of induction is helping me to prove this given statement actually. Okay? So you have to practice down better previous things. Okay? So if you are getting a bit hard time in learning this stuff, that means that you haven't worked on your previous stuff that we have covered actually. So we need to work on that. So you should work on that as well. ठीक है मेरे बच्चे? So this is what that we have to carry on and do. Okay. So I think these are enough examples for proving the principle of induction. So you have to do a lot of such calculations, such proofs in exercise, I think 4.3 and 4.4 and 4.5 actually. Okay, so I have identified some problems and I have left those problems for you to prove actually. इसमें कोई सवाल है तो बेटा पूछें जरूर, वरना फिर आगे चलते हैं. कोई सवाल नहीं है, आगे चलते हैं. एक और मिसाल करते हैं. Let's do another example actually. Let's do another example. ठीक है. So see, the previous things that we are doing are playing an important role in doing things stuff. This is stuff actually. Okay, so if you are keeping up with yourself with the previous things, you can prove it actually. You can do it. So here is a theorem or a lemma. So all of these are examples actually. I'm not interested in proving these theorems and lemmas. I just want to demonstrate actually that how this principle of induction is a powerful method to prove any kind of a statement actually, which is about natural numbers. So if you want to prove some statement about natural numbers, that okay, this given statement is true for some natural numbers or all natural numbers, you can prove it easily from the principle of induction. So for example, this is an example on page 123. So this says that for an integer or natural number, whatever you call it, n bigger than or equal to 1, okay, 3 divides n cube minus n. So that's a very interesting kind of a result actually. That for take any natural number and do the cube of it and subtract n of it, it's always divisible by 3 actually. Okay? You can quickly think of that. Okay, if I take 2, so 2 cube minus 2, so it's gonna be 6, and 6 is divisible by 3. Take 3, so 3 cube is 27, minus 2 is 25, so 25 is divisible. Is 25 divisible by 3? No, 3 got 24. 24 होगा, 24 होगा. ठीक है. So that's really the rule that we would like to prove. So see what power this method is giving to you, that अगर आप इनको, if you are proving these results for say 1, 2, 3, this is not going to be a general proof. So you have to prove this generally, and the method to prove such things generally is really the principle of induction actually. So let's do the basis step actually first. What we should do, let's do the basis step. By the way, we can give this statement a name that, okay, this statement is P of n, and I want to prove that the P of 1 is true actually. So what do you mean by P of 1 is true? Take this expression n cube minus n, substitute 1 into it, and see that 3 divides this expression or not. So let's see that 3 divides 1 cube minus 1 or not. So this is same as 3 divides 1 cube minus 1 is going to be 0. So is it true that 3 divides 0? It does actually. It does. It does. Keep in view the definition. Recall the definition. What is the meaning of A divides B? So A divides B if and only if I can find an integer k such that B is k times A actually. So B is a multiple of A actually. Now why 3 divides 0? Because 0 can be written as 3 times an integer which is
multiple
0 actually. Okay, so
0.
So therefore P of 1 is true. So this P of 1 is really true actually.
सर
जी जी
इसको एक्सप्लेन करें ना थोड़ा 3 डिवाइड बाय 0 3 डिवाइड बाय 0
नहीं, डिवाइड बाय 0 नहीं है ये कौन कह रहा है ये डिवाइड बाय 0 है? ये डिवाइड बाय 0 नहीं है, 3 डिवाइड्स 0 है, ठीक है। ये जो है बड़े हो जाओ अब। ये हमने पूरी पिछली क्लास में we talked about it basically that don't interpret this as A upon B. This is not A upon B. This means that A divides B. That's how you have to read it. Or B is divisible by A. That's what it means. This is not 3 divides. This is not 3 upon 0. ठीक है? ठीक है? V is divisible by A actually. So this is not 3 upon 0. And I really अभी explain भी मैंने किया कि भाई 3 divide क्यों कर रहा है 0 को? Because 0 can be written as 3 times some integer, and that integer is 0 itself actually. ठीक है? So 3 divides 0. So the P of 1 is true. So now go for the inductive step actually. ठीक है? So let's go for the inductive step. और inductive step में क्या होगा? So what we have to do in the inductive step? In the inductive step, always you have to take care. Assume that the given statement is true for P of k and prove it that it is also true for P of k plus 1. So assume P of k is true. That is what? That 3 divides k cube minus k. ठीक है? 3 divides k cube minus k. That is, इसका क्या मतलब है? कि 3 divides k cube minus k. इसका मतलब है कि there exists, I don't know, let's say an integer j such that k cube minus k can be written as 3j. Agreed? From definition of divisibility, keep this view. And now we want to prove what? So that's our assumption. Now we want to prove that P of k plus 1 is true. This is what that we want to now say that
existential. यहाँ पे existential क्यों लिया हमने?
क्या किया?
Existential लिया ना यहाँ पे for all भी है, वो क्यों नहीं लिया?
कहाँ पर? ये J जो है, ये जो J लिया है हमने,
जी जी,
नहीं तो ये तो डेफिनेशन से फॉलो करता है ना बेटा, ठीक है ना? ये तो समझ लेना, ये तो समझ
all ले सकते हैं ना?
All क्यों ले सकते हैं? All क्यों ले सकते? Is it 12 is equal to 3 times all numbers or some number?
ओके सर समझ आ गया।
it's ठीक है ना, जब मैं when I'm saying that 3 divides 12, this means there must be a number when you multiply that number with 3 gives 12 actually. ठीक है?
Okay,
So I'm saying that 3 divides k cube minus k. So this means that by definition there must be an integer j such that when you multiply that integer with 3 you get this number k cube minus k. And now I would like to prove that p of k plus 1 is true. That is, I would like to prove, what I would like to prove, that 3 divides k plus 1 cube minus k plus 1. That's what we would like to prove actually. Okay? So how to prove it? So let's think about it. So let's use some other color actually. So let's think about this k plus 1 cube minus k plus 1. Okay? What should I do? So see, my task is to use this fact to prove this fact actually. But in order to use this fact, I must have k cube minus k. But I don't have k cube minus k here. Can I have in some way k cube minus k here? Can someone give me a hint or something like that? How to get k cube minus k from this expression?
Sir,
इसको
k plus
expand
1 whole
करके
cube.
Expand kar dein. This is very good. So let's expand it. So when you're gonna expand it, what you're gonna get? K cube plus 3k square plus 3k plus 1 and minus k and minus 1. So what's gonna happen now? 1 and 1 will cancel out, and what you're gonna get? You get k cube plus 3k square. I don't know. By the way, cancel agar na theek hai. Okay, so let me do this clever
minus
step.
k.
Exactly, minus k karna chahiye. That's what I was thinking to write actually. Okay, so see, some people are really following it actually. Okay. So I can write this expression, rewrite this expression as k cube minus k. So this minus k is this k plus 3k square plus 3k. And what do I know about k cube minus k? It's equal to 3j. So let's put 3j plus 3k square plus 3k. And now what can I do? So I can pull out this 3 outside and j plus k square plus k actually. And let's give this entire guy a name that, I don't know, let's call it 3p, where the p, I or whatever, take j plus k square plus k. And is this an integer actually? The answer is yes, because I know
Yes, sir.
j is an integer, k is an integer, so this entire thing is
K is
an
integer.
integer actually. So what did I just proved? I proved that k plus 1 cube minus k plus 1 is equal to 3 times of some integer. So what does this shows? This shows that 3 indeed divides k plus 1 cube k plus 1. So that's what is really, the proof of this fact. So we proved it through induction that no matter what, what do you call, n you take, 3 always divides n cube plus n cube minus n actually. Okay? So you can see actually that the principle of induction works actually in a lot of cases actually. Okay, that if you have especially a statement about natural numbers and integers, so you can prove that statement are all such a statement through the principle of induction actually. Okay, and we're going to see that there are several things that are based on the principle of induction actually. ठीक है, is there a question actually? कोई सवाल है तो पूछें, otherwise फिर हम. So I think these are enough examples of principle of induction. Divisibility वाले भी कर दिए, so we did divisibility kind of problems, we proved identities, we proved inequalities through principle of induction, and we can get a lot of benefits out of it actually. Now I would like to move to a little topic, okay, which is really JJ. Someone want to say something?
इवन के लिए प्रूफ कैसे करें सर?
किसके लिए?
सर इवन के लिए कैसे प्रूफ करें? इवन के लिए सर मैंने एक एग्जांपल यहाँ पे किया था जो नहीं हो रहा था.
अच्छा, so give me that example.
सर वो बुक से ही है सर.
कौन सा एग्जांपल है? नहीं, इवन के लिए कौन सा एग्जांपल है? Tell me the page number.
सर थ्योरम, सर पेज नंबर 104, थ्योरम 4.22.
पेज 104 है and theorem है 4.22. Okay, ठीक है. So n square plus n plus 2 is always even actually.
ये ऑफ k plus 1 तक आ गया है.
k plus 1 तक आ गया.
हाँ सर, फिर इसको इवन शो कैसे कराएं वो नहीं हो रहा था.
देख लें. Let's do another problem based on it. Let's practice more actually on proving such things. Okay, so another thing that has came from one guy is that let's prove another theorem. By the way, the things that I have covered, they are not only from this section 4.2, but they you know, kind of, I have already done the section 4.4 and 4.5 as well, because there are the several examples that I have done it from the section 4.4 and 4.5 actually. So I'm assuming them to be done. So your task is now to do the exercises based on those actually. And 4.2 is really simple actually. So you can also do it easily. So let's prove this theorem actually, which says that for every n bigger than or equal to 1, no matter what natural number you take, okay, the number n square plus n plus 2, this number is even actually. Okay, this number is always even. So that's what we have to kind of prove actually. And you will see actually that this proof is not going to be much different from the previous proof that we did actually. So here's a proof. Let's first of all give this statement a name. Let's call it P of n. And by P of n, what do I mean? That take any natural number from 1 onward, n square plus n plus 2 is even actually. So let's see that why P of 1 is true. Is P of 1 true? Because if you take 1 square plus 1 plus 2, this is equal to 4, and 4 is an even number. So P of 1 is true. And now let's do the inductive step. Okay. So what we need to do in the inductive step, we have to prove, we have to assume that P of k is true. P of k is true. That is k square plus k plus 2 is what? Is even actually. Okay. So, by the way, if it is even, what does it mean? It means that k square plus k plus 2, whatever this number is, it should be equal to 2 times of some j.
2 some j.
Yes,
J is integer.
J is an integer. Okay, so that's what is the meaning of some number being even actually. Now let us show. Now let us prove that P of k plus 1 is true. True. That is, that what would be P of k plus 1 statement? That k plus 1 is square plus k plus 1 plus 2 is even. Okay, that's what we have to prove actually. And by the way, how can I prove now that k square plus k plus 1 plus 2 is even? So I have to, keep in view that I have to use this fact to prove this fact actually. So what should I do?
Expand.
Expand, expand actually. So let's expand actually. So if you're gonna expand, what you're gonna get? K square plus 2k plus 1 plus k plus 1 plus 2. And now, I don't know, if I rewrite this expression
separate k square plus k plus 2.
Subtract करने की जरूरत नहीं है. There is no need to subtract.
Separately, right?
Yes,
no.
Separate.
No, I'm saying separately.
Okay, yes, that's correct. K square, not 2k, k plus 2. So what is going to remain actually? So it's going to remain. So I have taken this term, say this term, and this term. All right. So what is going to remain is 2k plus 2. Right. Now by assumption, k square plus k plus 2 is equal to 2j. So this means this first expression will become 2j. So 2j plus 2 plus 2k plus 2 actually. And hence you can see that this is going to be
bidistributive.
Exactly. And then 2, and this is p actually. So we proved that this expression is 2 times of some p, where the p, which is j plus k plus 1, is an integer actually. So this completes the proof. This shows that hence k square plus k plus 1 plus 2 is even. And thus, you must write it, the principle of induction, P of n is true for all n bigger than or equal to 1. That is, that this n square plus n plus 2 is even, okay, for all what? For all n bigger than or equal to 1. That's really the recipe. So you see, this principle of induction works always. It really works always actually. No matter what situation you take, you just have to think a bit cleverly, use your previous knowledge and prove your given thing actually, the given statement. Okay?
Sir?
Did it?
Sir,
Yes.
can you do all the previous statements that we have did in 3rd chapter through principle of induction?
No, not all actually. I mean, you can't prove, I don't know. Okay. So here's the thing. There are things that you can prove and there are things that you can't prove. For example, you can prove that, for example, x power times x power n multiplied by, say, x power m equal to x power n plus m. You can prove it through induction actually, where n and m are, say, natural numbers. Okay, you can prove this through induction, but not all statement. Obviously, I can't prove that x plus y square is equal to x square plus 2xy plus y square. Okay, I can't prove such a statement. So or I can't prove that if A is less than B, then A plus C is less than B plus C. Okay. So,
Okay, sir.
so this principle of induction will work only on those kind of situations where the natural numbers are involved in a given statement actually. So if the
And sir, is it important to be if-then statement?
Yes, it should be. It's really
Okay,
important to be the if-then statement actually. Okay. Even you see that, I mean, there is no if-then in this given statement, but you might say that, okay, where is the if-then here? There is an if-then here actually.
Yes, sir.
So it says that if, you can rewrite it, if n is greater than or equal to 1, then n square plus n plus
Yes,
2
sir.
is even actually. So there is an if-then statement. Okay, there is an
if-then.
So you can prove all kind of statements, the theorems, okay, that are about the principle of induction through this actually. Okay, through principle of induction about the natural numbers. So if a statement involves natural numbers, you can certainly prove it through the principle of induction.
Sir,
Yes.
when it is given as n is greater than 0, for the basic step, we have to use n equals 0 or n equals 1.
Okay, so n is greater than 0 means that you have to obviously substitute. You have to start from n equal to 1 actually. Yes, you have to start, and because obviously 0 is not a natural number. Okay.
Okay, sir.
But the science people say so, that's a natural number, but we are mathematicians, we don't agree with them. Okay.
So can we write that if n is greater than 0, then n must be greater than or equal to 1?
Yes,
and it's a natural number.
Yes, if it is a natural number. Okay, so not everything that is greater than 0 is a natural number. Okay, not everything that is greater than 0 is a natural number. But
okay,
if we know that n is a natural number and it is greater than 0, this is same as that n, it can be any natural number. It could be bigger than or equal to 1 actually.
So when it is given n is similar or greater than 0, is it same as that?
I mean, even if it is given greater than or equal to 0, for example, you have to prove a statement. In other words, for example, this n square plus n plus 2 is even, like this is true not only for n greater than or equal to 1, but it is also true for n greater than or equal to 0. Isn't it? Because if you take p of 0, what it would be? So it's going to be 0 square plus 0 plus 2, which is even actually. Okay. So I don't want to complicate you too much actually, but the principle of mathematical induction, can not only be applied to the situation when the n is a natural number, it can also be applied to the situation when n is an integer actually, whether it is positive, negative, whatever. Okay, but at the moment in this chapter, in this book, we will be only limited with the cases, with the cases that when the n is natural number actually. Okay, it's some kind of a natural number. We'll not talk about the integers and so on. Will not go beyond the natural numbers actually. So what are some of the
then जो अभी हमने proof example किया था even number का, उसमें भी तो integer involve हो रहे थे, वो भी हमने induction के जरिए proof.
In integer का involve होना in definition is different thing, but the claim should not involve integers actually. हमारे केस में यहाँ पर यानी जो statement है, the statement of the problem should not involve integers. So we are not going to talk about the statements about, and I'm not going to talk about the p of n when n is an integer actually. ठीक है? हाँ, integers कहीं, so integers can come up somewhere in proof actually, that's fine. ठीक है? But we will at the moment
All right,
just
sir.
restricted only for the statements when the the numbers are natural numbers. Okay, all right. So I was
ठीक है.
thinking to do few more things, but I must restrict myself to. So have you seen some of the more interesting things actually that, for example, that involve natural numbers? Some statements that you have encountered previously about natural numbers. So say for example, you have seen binomial theorem actually, huh? So how many of you people have seen binomial theorem? X plus y power n
Yes, sir.
is equal to what? N choose 0, x power n, y power 0, n choose 1, x power n minus 1, y power 1, plus so on and so forth. And you got n choose n and x power 0 and y power n actually. Okay, so that's what is really, what do you call, like this is true for all natural numbers and for all x and y, which are real numbers actually. X and y are fixed, but like this is true for all natural. No matter what power you take, you can always expand it. Now, if you see, this is also, I can also treat this statement as P of n. And I can try to prove, for example, this statement for what? For natural numbers actually. So shall we prove it? So let's try to prove
Yes,
it.
sir.
Let's try to prove it, okay? The proof is going to suck a little bit, but don't worry. It's really it's nice actually. So let's do the basis step. So what we need to do in the basis step actually, sorry. So we need to show that the P of 1 is true. What do I mean by that? If I take, say, x plus y power 1 on one side, and on other side I take, say, 1 choose 0, x power 1, y power 0, plus what would be the last statement? 1 choose 1, x power 0, y power 1. The both statements are same actually. What is 1 choose 0? Does people remember the formula? N choose R? The God-given formula, which we never understood that from where this formula came. N factorial, R factorial, N minus
n
R
minus r.
factorial. So we know this formula. So what would be 1 choose 0? So you can show that 1 choose 0 is really 1, and 1 choose 1 is also 1 actually through this formula. And what is something power 0? It's also 1. So see that this side becomes what? X plus y as well. So what does it mean? This means that these both things are equal. Okay? These both things are really equal actually. So if they are equal, what does it mean? This means that the P of 1 is true. The P of 1 is true. All right? Okay. So what we should do next? We should now think about doing the inductive stuff actually, that okay, if the P of k is true, then the P of k plus 1 is true actually. So suppose that P of k is true. That is, what do I mean by that? That if you take x plus y power k, this is equal to k chooses 0, x power k plus k choose 1, x power k minus 1 times y plus so on and so forth. plus the last term is going to be k choose k, and x power 0, y power k. And what would be the previous term? For the sake of simplicity, let's k choose k minus 1, and you're going to have x power 1 and y power k minus 1. Agreed? That's
Yes,
your,
sir.
that's p of k. And now we want to prove, that p of k plus 1 is true. This is what that we want actually. That is, we will like to show that if you take, I don't know, shall I write it here? Maybe somewhere here, that x plus y power k plus 1. So you're going to get what? K plus 1, choose 0. So wherever you have n, just replace it by k plus 1. Okay, so in this expression, this entire expression, in this expression, replace k plus 1 wherever you have. So k plus 1, 0, you're going to get what? You're going to get x power k plus 1, and up to the final term is going to be k plus 1, choose k plus 1, okay, times y power k plus 1. Okay, so there are going to be several terms in between. So that's what we have to prove. This is what something that we don't know. Now, can you give me a suggestion how to start? From where we should start? Keep in view, always the key step is to, can you express the k plus 1th statement in the terms of kth statement actually? Exactly. So in other words, can I express this thing in the terms of this so that मैं इसे इस्तेमाल कर सकूं? Okay. The answer is yes, actually. Why not? So let's do what? So let's do x plus y power k plus 1, and this is same as x plus y power k times x plus y. Okay. And then substitute the value of x plus y. So let me write it. So this is going to be a long expression, but let me write it. So it's going to be k times 0 of x, k choose 0 of x plus x power k plus k choose 1 x power k minus 1 y plus so on and so forth. The second last term is going to be k choose k minus 1, okay, and I don't know, x y power k minus 1, and the last term is going to be k choose k and y power k. So that's really is the bracket multiplied by x plus y. Now how can I multiply this? That, okay, take this, say for example, x and multiply with the entire expression, and then take y and multiply with the entire expression, right? So let's take x and multiply with this entire expression. So what you're going to get? You're going to get k choose 0. So it's a bit laborious work, but it's worthwhile doing it. X power k plus 1. और यानी if you do it once, तो फिर आप कसम उठा सकते हैं कि हमने जो है वो Binomial Theorem का proof भी पढ़ा है. So you can really satisfy yourself that you just, you know, haven't memorized the Binomial Theorem. You know the proof of it, that why this is true, on what basis this is true actually. Because you remember, I always say that, you know, question everything that you have learned in your previous mathematics. That's what this course is all about, actually. That okay, how to think about the basic things. Okay, so multiply x with this expression. So what are you gonna get? X power k y plus so on and so forth, plus this expression, this x is multiplied with this. What are you gonna get? You're gonna get k choose k minus 1 x square y power k minus 1 plus the last term is going to be k choose k and x y power k actually. Okay, plus then I have to multiply y with all of these. So let me use some other color for doing it. So when I'm multiplying y with this, so I'm gonna get what? K choose 0, okay, and x power k y plus k choose 1, x power k y square plus so on and so forth, plus y multiplied with this last term is going to give me what? K choose k minus 1 times x y power k plus so on and so not so on and so forth, but k choose k times what are you gonna get? Y k plus 1. Okay, so this is what that we have, get. Now I need suggestions. Okay, I need suggestions that what should I do? Oh, sorry, I just want to get rid of this. I need suggestions that what should I do? What should be my next step actually? The next step should be to really, okay, so do you have any suggestions? What should we do?
सर P of k को अलग कर सकते हैं ना अभी?
P of k को अलग कर सकते हैं? वो अलग तो हो गया ना?
Yes sir.
So अलग करके हमने वैल्यू सब्स्टिट्यूट कर दी, P of k इस्तेमाल हो गया. So we have used the P of k actually, because when I substituted x plus y power k replaced by this, I have used the P of k. So then what should be the next thing actually? The next thing should be, here's the key thing. The next thing should be to combine the like terms actually. So for example, let me write this long expression here. Okay. So what is the first term? The first term is this. K choose 0, x power k plus 1 plus. Now you see you have x power ky. So is there any other term with this x power ky? The answer is yes, it is here. So if I put these together,
Yes, sir.
if I add these two terms, so what I'm gonna get? I'm gonna get k choose 1, k choose 0 plus k choose 1 multiplied by x power k and y. Okay, keep in view that like this is a separate stuff. Okay, so what we should do next? So similarly, we should think about okay, so no, I don't need this. Why? Okay, so what we should do next? So next, say let's combine which term? Combine, say, this term, okay, which term, I don't know, this term, maybe I should use a different color, this term with which term, I don't know why the color is not changing, okay, this term with which term, can you tell me the term that is so what we should do. Where is x power k y square? Will there be a term like x power k y square?
मतलब बीच में हो शायद जो नहीं लिखा हमने.
बीच में हो शायद. Yes. So it's gonna be basically here actually. So here's the thing. इसके बाद वाली term क्या होगी? What would be the term afterwards? K choose 2 x power k minus 1 and y square actually.
Y square.
So you're gonna get a y square term, but this power should be k minus 1. Have we done any silly mistake actually? I think no. So here's the thing actually. Okay, let me tell you. So forget about this in between terms. Just think about the extreme terms actually. Okay, just think about the extreme term. What would be okay? What are some other terms actually that you should for now? So for example, the very last term is going to be this actually. Okay, so let's settle it down. So you have k and y power k plus 1. Is there any other term that is agreeing? Yes. So this term is the same as this term actually. The second last term of the above expression is same as the second last term of this. So if you put them together, what are you gonna get? So you have k choose I don't know, k plus k choose k minus 1 times x power what? xy power k. xy power k. So that's what you're gonna get. Okay, so you know, forget about the in between terms. Okay, so you can settle it down. You can always put them together and you're gonna get this actually. Now here is my claim actually. Why my claim is that this is what is really the required expression that you want. But you're gonna say, okay, how this could be the required expression? Because if I substitute say k plus 1 here, there must be k plus 1. Okay, so you have a k plus 1 here, fine, but there's no k plus 1 here. But you can prove actually, okay, you can prove actually that if you compute k plus 1 choose 0, this is going to be 1 by definition. And this is same as k plus 1, this is same as k choose 0. So in other words, on the place of k choose 0, if I replace k plus 1 choose 0, there is no difference actually. The expression is still same. I don't know whether you can see this yellow guy or not. K plus 1. Okay? Similarly, let's think about the last term. What would be k choose k? So you can calculate that k choose k is 1. But you can also calculate that k plus 1 choose k plus 1 is also 1 actually. So if it is 1, I can rewrite this expression as k plus 1 choose k plus 1 actually. Right? And how about now these terms? What should I do with them? So do you remember any identities from your permutation combination knowledge actually? Any theorem, any identities that you remember? Identity yaad nahi hai. So let's recall this identity, and you can prove it actually very easily, that if you have n choose k, okay, and if you add into it n choose k minus 1, this is same as n plus 1 choose k. So n choose k plus n choose k minus 1 is equal to n plus 1 choose k. Verify this identity. Okay, verify it. Don't trust on me. Verify that this is true. Calculate this side and this side, add them and see that whether you get this or not. So if this is true, by this identity, what would be this quantity? This quantity. So this is going to be k plus 1, choose 1, right? And what would be this quantity? This quantity is going to be k plus 1, choose k actually. And this is precisely what you want. This is precisely what you want, okay? So if I get rid of all these color and try to write it in a single color, then the first term is k plus 1, choose 0, x power k plus 1. And the second term is k plus 1, choose 1, x power k, y, plus so on and so forth. The second last term is k plus 1, choose k, x, y power k. And the last term is k plus 1, choose k plus 1, and y power k plus 1. And we are the happy man. That's really the proof of mathematical, of the binomial theorem through the mathematical induction. I know it's a bit messy. You can also find this proof in book actually. So I think he has proved it somewhere. So if you want to see it from there, you can also see it from there. But I hope that you also got some sense of it. इसमें कोई सवाल है आपको? Exercise 20 है 4.3 में. So in exercise 4.3, if you see the problem 20, it's really on the binomial theorem actually. Okay, if he's trying to prove the binomial theorem through this. So what are all these examples are showing to you that all statements that involve natural numbers, okay, can be proven through the mathematical induction actually. Okay, all the statements, such statements can be proved through the mathematical induction. So even the binomial theorem actually. Okay, in the next term, or maybe if we'll get time, we will see actually that all these messy results that you have. Okay, so kitna mushkil hai. So it's really time taking to prove through the mathematical inductions such identities. So what you can see later in, for example, in your probability theory course. Okay, why not? Okay, this goes crazy. Anyway, so all these can be proved through the story proofs actually. You're going to learn another kind of proof types actually. It's called the combinatorial proof. I call them story proofs actually. So create a story and prove your mathematical identity. You're going to learn this in probability theory. Anyway, so my point is this, that I hope you got some sense of mathematical induction. The essence of the mathematical induction is give me any statement about natural numbers. Okay, could be equation, inequation, inequality, could be anything. Okay, it could be anything actually. Okay, so give me anything about natural numbers, then I can prove it through any statement about natural numbers. I can prove it through mathematical induction. And what is a step? First, should you prove it for, say it is true for P of 1, and then assume P of k, and from P of k try to prove P of k plus 1. That's what is really the essence of it actually. And I would highly recommend that the proof of the principle of induction, you should also learn it actually. That okay, this is what is it seems a bit messy, but it's not that messy actually. If you still think that you have troubles, you can set up time with me and we can have a session in which we can do discussion over anything you like actually, including all these proofs actually. Okay, so So, and any question or anything else that you want to do, that you want to have? कोई सवाल है तो जरूर पूछे बेटा.
Sir, I have a question from previous classes.
Sure, sure, sure.
Sir, whenever we multiply 0 with any number, we get always 0. What is property behind it?
What is the property behind it? So that's
Yes,
Multiplicative identity.
Not the multiplicative identity. Not the multiplicative identity, but it's a property of the zero actually, that if you multiply the zero with an integer, it really gives you 0 actually. Okay? But you can prove this identity itself by I don't know, distributive property and the combination of distributive property and so for example, I want to prove what is 0 times n actually. Okay, so that is my favorite number, that okay, if I multiply 0 with some number n, I want to conclude that what would be this number. So, you know, 0 is 1 minus 1. You agree with me?
Yes, sir.
Apply the distributive property. So it's going to be 1 times n minus 1 times n actually. So you get n minus n. So distributive property and then the additive property.
Additive inverse.
Additive inverse actually. Okay. So you have it. So it's really a consequence of it actually. So why this is not a fundamental property in the list of the properties, because this is something that you can prove through distributive law and the additive inverse property. So there is no need to, you know, include it in you know,
okay, sir,
the list of the basic properties. So you can deduce it. You know, Hamid had said that summation convention, we haven't covered those. We will do it actually. I intentionally left this because I want that's a really important topic actually, because you have to deal with in your future discussion this summation convention and all that stuff actually. So I'll do this in next class. Okay. So I didn't started this topic of summation convention intentionally, because I didn't want it to bore you with you know, with a new topic actually. So I just said that okay, we have done a lot of examples on mathematical induction, so let's do some more examples actually. Okay. By the way, after today's discussion, I'm not doing the section 1 of the chapter 4, so leave it. After today's discussion, you should be able to do some problems, selected problems for 4.2. In fact, all problems of exercise 4.2. Okay. But I have just selected some actually for you. You can see the list on the LMS. You should be able to do the problems 4.2, exercises from 4.2, not exercise 4.3 because we haven't yet covered it, but you can do the problems from 4.4 and 4.5 actually. So you can do the problems for 4.4 and 4.5. Okay. So we will do the 4.2 section. जी
सर 0 से सर जो मल्टीप्लाई करते हैं किसी भी क्वांटिटी को, सर वो 0 क्यों आता है सर? इसका एक ये भी रीजन है ना कि हम 3 से मल्टीप्लाई करते हैं 2 को, तो सर हम उस 3 को 2 बार ऐड करते हैं ना, 3 + 3.
Yes, you can also call it.
और सर अगर हम 0 से मल्टीप्लाई करेंगे तो अगेन वो जो हमारी 0 क्वांटिटी है सर, उसको हम 0 अगर 3 को मल्टीप्लाई करते हैं 0, तो 0 + 0 + 0 अगेन आंसर 0 आएगा. सर ये ऐसा कह सकते हैं?
Yes, this is also a correct way to say that why my favorite number is a thing. 0 times you know 3 is 0, because 0 times 3 I can interpret as that okay, add the 0 3 times actually. Okay, but I would say this is a more general proof actually. ये ज़्यादा general proof है. Can someone tell me that why this is a general proof? कोई बताएगा कि why this proof is a general proof?
सर क्योंकि ये हम हर नंबर के लिए कर सकते हैं ना, हर नंबर के लिए।
Exactly. I mean, your explanation would not work for when the 0 is multiplied by 1/2. Okay, because what would be the meaning of adding 1/2 times 0? Okay, so this above argument can work for any n.
Yes, sir.
Could be natural number, integer, it could be fraction, whatever. Okay, so it's always going to work actually. While this is good actually. I like it. Okay, so this is not something that is that I'm disagreeing with, but you can have a more general proof. So if you have a proof for a which is not general, then always prefer the general proofs. ठीक है मेरे बच्चों. If you have any other question, if you want some personal times, ऐसा भी हो सकता है कि sometimes you think that कि अच्छा मुझे यार दूसरों के सामने पूछने में थोड़ी सी शर्म आती है. I really get shy when I ask in front of others. You can write to me and we can have a one-to-one or maybe some sessions of Zoom sessions in which you can ask the questions the way you like actually. Or if you think that you need additional time to solve some exercises, I hope you are free at home. I am free at home, so we can have more and more discussion. ठीक है? वो जो आप कैंटीन में तबाह बर्बाद करते हैं टाइम अपना, उस टाइम को आप डिस्कशन के टाइम के लिए ये जो है, you can keep it.
Okay.
Yes, sir. In chapter 3, we feel little bit curious in the exercise
So if you have
so
queries, you should constantly discuss actually. ठीक है? So that in the final part you shouldn't have a too much burden of exam.
Yes, sir.
ठीक है? So I hope that you liked this new proof method, the method of proof things, the principle of induction. Okay, because this is the method actually, and you liked it, and try to practice on it. Try to solve some little problems first. Try to solve some easy problems and then gradually go to the more complicated kind of problems. ठीक है बेटा? Wish you good luck. I will upload this entire discussion on LMS actually, so you can also watch it from there actually. So if you wish. ठीक है? Good luck.
Okay, sir. Thank you.
Allah Hafiz. Good luck.